All right, so what we want to do, and pretty much, I mean, every case I can think of, and there are exceptions to these things, but and I talked about this yesterday in detail, so I don't think I need to go too crazy with it again today. But the idea is that we're looking to make a determination of whether a series converges or diverges. All right, not necessarily what it converges or what it converges to. All right, technology can figure out the actual sum, provided we can tell the technology there is a sum to be found. All right, so the issue is there's a general lack of understanding and misconceptions, everything that come into play when dealing with series as opposed to sequences. All right. So when we talked about the partial sums yesterday, that's something I want you to kind of keep in your mind. It was such a terrible experience that it's something that you probably don't ever want to do again. And what that is you list out, let's say, the first 10 terms of the sequence, all right, which would be what you would get if you plugged in a 1, then a 2, then a 3, all the way up to a 10. Now, what a sum would be actually adding those together. But if I wanted, let's say, the third partial sum, that's not the third term of the sequence. That's not what I would get if I plugged a 3 in for n and simplified. Right? It's what I would get if I plugged a 1 in for n, a 2 in for n, and a 3 in for n, simplified all those, and then added the results together. All right? So if I were to say something like find the 10th term of the sequence, that's not terrible. You're happy to do it. If I were to say find the 10th partial sum, your first instinct should be, let me get my calculator, because that's not going to be as easy as I think. You're not just going to plug in a 10, you're going to plug in a 1, then a 2, then a 3, then a 4, then a 5, 6, 7, 8, 9, 10, get those results and then add them all together. All right, much different experience. That's why I showed you that table technique with the stat editor, all right, because that's going to do for you what you want, hopefully, to avoid doing by hand. All right. So we have two types of tests that we're going to learn about initially. One is the arithmetic series test. That's kind of a one-off. Like we're going to talk about it for a second, then never talk about it again. Geometric series test, that's going to come up very, very frequently. All right. Arithmetic series converges if and only if a sub 1 and d both are equal to 0. All right, so if you really think about what that means, in either of these two forms, it's telling us that the only way you're going to get a convergence on an arithmetic series would be if it's the sum of 0. All right, otherwise it'll never converge on a particular value. All right, so if you were to take any linear function, because that's what an arithmetic series is, it's in the form of a linear function. A linear function, whether it's positive or negative with the slope, it's always going to be changing, whether it's a constant rate of change or something like, well, it would be constant rate of change, but let's say a rate of change that's a numerical value like 2 or 1/2, or a rate of change of 0, but the y-intercept being equal to, like, let's say 3. If that's the case, then no matter how many steps you take out, you're always going to be increasing the value. All right, so for every additional step, I'm going to get more or less depending on what the slope is. All right, but geometric series tests, that's a little easier to work with. All right, provided you're in the right form. Now, I write each of these series in different forms because depending on the textbook, the teacher, whatever, you might have seen it in different ways. In pre-calc, algebra 2, or college algebra, if you did anything with sequences and series, you might have been told it didn't matter whether your lower bound was equal to 0 or 1, or 2 or 10 or 15. Well, it does, because if we're limiting our domain to a set of positive integers, the lowest positive integer is equal to 1. So I would want to be going from 1 to infinity if I'm dealing with an infinite series. All right? So in every case where possible, I want to have it in a form where the lower bound of the summation is equal to 1. All right. So if you see it online in a textbook, OpenStax or otherwise, go with the one where the lower bound is equal to 1. Otherwise, you'll find yourself adjusting it so that it is equal to 1, which is not always the easiest thing in the world to do. All right. So I need to determine whether the series is going to converge. Now, we learned a couple of pages ago some rules associated with this, but I basically streamlined it here. Geometric series diverges if your R value is 1 or larger. It's going to converge if your R value is less than 1. All right, or specifically the absolute value of R is less than 1. All right, now let me just take a second and talk about what that absolute value of R means. All right, so this goes back to college algebra, algebra 2, whatever. This equates to, so it's the same as R being between -1 and 1. All right, so when you have an absolute value in inequality form, there are rules that come into play. This is the rule that we care about right now. All right. So if our R value is between -1 and 1, we're in good shape. All right. So I want to rewrite this, and it is the same problem we did yesterday, so it should seem very familiar. I'm going to rewrite it as 3 times 2 to the -nth power, so I'm bringing the base and exponential up, but negating the exponent. If I have a negative exponent, that tells me to take the reciprocal of the base. So that's the same as saying 3 times 1/2 to the nth. All right, so it's pretty close to the form that we want it to be in. N minus 1 instead of n, or n instead of n minus 1. That's not really the part that's important, because I can always adjust this so that it has an n minus 1 power. That's not really the part that I'm overly concerned with. It's whatever the R value is. All right? And I'll show you how to adjust it in a sec. So R is equal to 1/2. So what we would say is the series converges by the geometric series test. All right, so your conclusion statement is always going to have 3 important parts. 1, whether it's converging or diverging. 2, what test do you use to make that determination? And 3, what condition related to that test allowed you to draw that conclusion? All right, so the series converges, so that's the first part. By the geometric series test, second part. And you could say because, you could say with, you could any way you want to, or just make the statement. I'll say because the absolute value of R is less than 1. All right. So, like I said, I'll show you how to rewrite the rules in different forms later on. But for now, it's just, does it have the same general structure? Yes, we're good. All right. So for the next one, well, right off the bat, you look at it and say, well, it looks very similar to A, but it doesn't have this, it's not quite the same in terms of the characteristics. The only thing really that we would need to change for this one would be to throw out a 1 in front. All right. And so here, the R value, so now it has the appropriate form. The R value is 3/2. Series diverges by the geometric series test because the absolute value of R is greater than or equal to 1. All right. I'm big on the abbreviations. So, I mean, you could write out geometric series tests. And we'll also get to alternating series tests and limit comparison tests and everything, ratio tests, root tests. And like, the only ones that I say that you can't overly abbreviate would be ratio test and root test, because they would both abbreviate to RT. And they're similar enough to one another in terms of their structure that it's easy for one person, for actually anyone, to make a conclusion thinking that they're using the ratio test when they're really using the root test. All right, so that's the only exception. But AST for alternating series test, GST. Like I said, we're not going to use arithmetic series test, so there's not going to be any confusion there for AST. Right? So anyway, let's say I wanted to write this summation in such a way that it had an n-1. All right, and this is why it doesn't matter whether or not you have a -1 and n-1 in the front or otherwise. Right? If I consider what my first term of the sequence would actually sequence here would be, all I would have to do is plug in a 1, right? If I plug in a 1, I get 3/2. If I plug in a 1 here, I get 3/2 to the 0th power, which is 1. Well, I don't want that. I want 3/2. So I would throw a 3/2 in the front. All right. So same summation, just slightly different form. If I plug in a 1 here, I get 3/2. If I plug in a 2, I get 3/2 to the 2nd power. I'm going to get 3/2 times 3/2 to the 1st, which is the same as 3/2 to the 2nd power. All right, so ultimately, I'm going to get the same thing. Now, since the ratio test, the geometric series test is based strictly on what the R value is, once you get it in one of these forms, it doesn't matter, because in either case, my R value is going to be equal to 3/2. All right, so it doesn't matter which way you write it, as long as you can clearly identify the 3/2, or the particular R value. All right. Oh, for the first one? Like, how did I come up with it from here to here? So we have a negative exponent. A negative exponent tells you to take the reciprocal of the base. So this would be 2 over 1, but if I take its reciprocal, that becomes 1 over 2. All right, so the nth term test for divergence. So specifically for divergence. This one, you know, it's easy enough to do. It's based on stuff that we've done before. It's always a starting point whenever you're trying to evaluate a series. If your series diverges, it doesn't matter what test you use in order to get you there. All right, so whether you use the geometric series test, the nth term test, or any of the other ones that I mentioned, once you've demonstrated that it diverges, you're done. All right. Convergence can often be more challenging to figure out. So what we often do is use the nth term test to start off to see if maybe we can sneak our way through to getting divergence, and then just call it a day. All right. So what does that mean? Well, it's kind of like a limit problem back in Calc 1, where you know that the first thing that you're supposed to do is plug in the limiting constant. Like plug in the number. You plug in a 2. And then you see what happens. But then every time you took a test or a quiz, that was like the only technique that didn't work. So it got to a point where that was a complete waste of time. So you know that they're going to be more challenging than that. He's never going to put a problem on a test where you just plug the number in, right? So you disregarded it. And then it showed up on a test at one time. And you tried every other technique for evaluating a limit, every strategy you could think of, didn't work, and then when you got the test back, it turned out that all you had to do was plug in a 2, and you were kicking yourself. All right? This falls into that category where it doesn't work so frequently that you disregard it, and then when it comes up on a test as the way that you're supposed to do it, you never even think to bother trying it. So I'm going to actively encourage you to try the nth term test in every situation. No matter what the question's asking for, try the nth term test first, see what it gets you. In most cases, it's going to be inconclusive. But then once you've tried the nth term test, then move on to the other stuff, all right? Because you don't want to throw away a 5-point question that's going to be a gift on the test because you're not even going to consider the nth term test as an option. All right, so what is the nth term test? If the limit of your sequence, all right, so we're going to use a characteristic of a sequence to help us make a conclusion about a series. So if the limit of the sequence as n approaches infinity is something other than 0 or dne, or it is equal to dne, so that's a little unclear. So not equal to 0 or it does not exist, then the series diverges, all right? So basically, if you get a number, so if you get some finite value, or if you get dne, then you're looking at a diverging situation. All right, 0 is a bad number in this case. So before, when we were finding limits, if you got 0, that was fine. It meant it converges. It converged to 0. But we're looking to make a determination of whether the series converges or diverges, not whether the sequence converges or diverges. We're talking about the sums. All right. So if you get, so really the only bad value here is 0. Because if you get 0 from the nth term test, it doesn't mean it converges, it means that it's inconclusive and you got to do something else. So what is the nth term test? Basically all the stuff we were reviewing in the first half of this class. Find the limit of your sequence as n approaches infinity. If you get 0, it means you got to do something else. If you get something other than 0, it means it diverges. All right? That's what that little notation means. Question?
This is also called the Divergence test, right?
Correct. So, limit. So here's my a sub n. I want the limit as n approaches infinity of my a sub n. I'm writing this in shorthand because it's easy enough to do that we don't actually have to rewrite the entire function. This one, a little different story, so I'll take you through that. What is the limit of this a sub n as n approaches infinity? Not infinity. I may have heard it. Not 1, 2 over 3. All right. So what you're doing when you're finding a limit of a ratio, you look at the powers. All right. So if the powers are the same, find the ratio of those leading coefficients. All right. So the degree of the top, degree of the bottom. All right. Degree is the highest power on the top, or the bottom, doesn't matter. So if those degrees are the same, take the 2 leading coefficients and divide them. That's your limit. If the power, the degree on the top is more than the one on the bottom, then it's infinity. If it's less, or some kind of infinity, it could be positive or negative infinity. If the power on the top, the degree on the top is less than the degree on the bottom, that means the denominator is going to win the race to infinity. If that's the case, then it's going to go to 0. All right. So if this were, let's say, 3n squared on the bottom, this would go to 0, and it would be inconclusive. But it is conclusive. The series diverges by nth term test. The limit is not equal to 0. You could also say the limit exists. If you want to say the limit exists and is not equal to 0, that's fine. And it's a little more than probably you would need, but again, converge or diverge, the test, and the characteristic of the test that led you to the conclusion. The second one, limit as n approaches infinity of n factorial over 2n factorial plus 1. All right. Believe it or not, this is going to have, we're going to follow the same procedure for this one as we did in part A. I'm just going to expand it a little bit. All right, so the general rule for a factorial is n times n minus 1 factorial. So we're always multiplying by 1 less than the number that you have. So if I were to start with a 5, the next one would be 4, 3, 2, and then eventually 1. All right? But if I'm starting with n, I don't know how many terms there are going to be because I don't know what n is. If n's infinity, then there's infinitely many terms. All right? If n is 10, then there's only 10 terms, or 10 factors. So all I could do here is say, all right, I know it's going to be n times 1 less than n, then 2 less than n, then 3 less than n, and then eventually it'll get down to a 1. All right? But I just want to learn from the process here. And let's say I'm just dealing with these. If I were to distribute this out, what would the degree be? What would the highest power be if I were to distribute all this out? 4. Yeah, because all I'd have 4 n's, right? I mean, there would be some n cubes, n squared, n to the first, and some constants in there, but it would begin with an n to the 4th. So this whole top, we could look at this as n to the 4th plus blah, blah, blah. 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 Now, on the bottom, it's going to have an n to the 4th also, right? It's made up of the same ingredients, but there's a 2. 2n to the 4th with several blahs afterwards. And then the plus 1. But as it turns out, the plus 1's irrelevant, right? Because all I care about is the term with the highest power on the top and the term with the highest power on the bottom. Now, is this necessarily going to be n to the 4th? No. Because I might have an n minus 4, n minus 5, n minus 10. But whatever I have on the top, I'm going to have on the bottom too. So if I had an n to the 10th up top, I'd have a 2n to the 10th on the bottom. All right? So the powers, no matter where I am in the progression, the powers are always going to be the same. So that tells me to take the ratio of the leading coefficients, and so that's going to give me a limit that's equal to 1/2. All right. Now, you can fake your way through that. Because I'm telling you, again, if you're in doubt, put it in your calculator. But you still need to justify it. So you still need to come up with the limit. All right? How you come up with that limit short of cheating is up to you. All right? So therefore, the series diverges by the nth term test and again the limit is not equal to 0. All right, next up, this is the beast. There are at least 3 ways to do this one, and one of them is the calculator. Another way is to try direct substitution, see what happens. All right, so we're looking at the limit as n approaches infinity of 3 to the nth minus 2 over 3 to the nth. The third way is to actually simplify it. Algebraically, if you break up your fraction, you can create a geometric series out of it. But I'm not going to do it that way. All right. If I were to plug in infinity for n, I'm going to get infinity over infinity. That's my license to use what technique for limits? L'Hopital's rule. All right, which may not be what you want to do. It really is just a question of, I mean, do you know how to find the derivative of 3 to the nth? If the answer is no, don't do it this way. All right, if you do, then go for it. All right, do we know the derivative of 3 to the nth? It's 3 to the nth times what? Not n. ln. Exponential is always repeat the exponential, multiply by the derivative of the exponent, which would be 1 in this case, multiplied by the natural log of the base. Natural log of 3. ln 3 in this case. So on the bottom, you're going to get also 3 to the nth times ln of 3. All right, the negative 2 is going to zap away. Derivative of negative 2 is equal to 0. Ah, 2 like quantities. The limit as n approaches infinity of a constant is in fact equal to a constant.
Like you were saying, you could have also split the fraction up.
Yep.
1 minus really 0.
1 minus 0 gives you the 1, yep. All right, so series diverges by the nth term test limit's not equal to 0. Now, we didn't have any examples here where the limit did not exist. If that were the case, you would say the series diverges by the limit by the nth term test. The limit does not exist. All right, so you know, I didn't feel the need to throw an example in there just to address that component. All right, but you can see hopefully that we're applying the skills that we've been reviewing the last couple of days related to limits. It's just a shame because it's like first couple of weeks of Calc you do limits, and then the very end of Calc 2 you do limits again. And it's like in the middle it's like where's your practice and review? Well, it's left to you to do, but you know how many people actually do it? I don't know. Some people do. And then if you're taking Calc 3, it'll be like halfway through the second unit maybe. Oh, the way I teach it anyway. So we'll see. I usually do Calc 3 in the spring though, so still wait a year, less than a year. No limits in that. They don't like limits. All right, so we're going to also learn about the telescoping series tests. So today we'll get through the integral test. All right, so the telescoping series test and the integral test. The integral test is very nice because it ties together all that improper integration stuff with what we're doing with series. So it's kind of a nice component. Telescoping series is kind of cool. You know, it's a very particular circumstance, and unfortunately, it can be one of those things where it's like, dang it, it's like the one category or the one type of question that I didn't prepare for on the test, because like it's very specific. Right? What happens is if you were to expand out a telescoping series, or you expand out a series, you'll see that there'll be consecutive values that are opposites of one another, and then they'll cancel out. And what ends up happening is you are only left with the first and last term of the expansion. And if you find the limit of that remaining collapsed form as n approaches infinity, that actually gives you the sum. But again, we just care about whether it converges or diverges. So a telescoping series converges if everything cancels out except for the first and last term. And under any other conditions, it diverges. All right, or it's just not a telescoping series. All right, so I'll show you actually how to find the sum on top of that. So what you'd have to do is start plugging in values. It's really quite fun. So you plug in a 1. You'd be looking at 1 over 3. All right, so plugging in a 1 for n, so 2 plus 1 is 3, minus 1 over 5. So that's what I get when I plug in a 1. Then I plug in a 2. You'll get a 1 over 5 minus 1 over 7. Now, it's nice in that you can kind of rely on some characteristics here. You can see that we're doubling up some values. The first value is singular. It doesn't happen more than once. But then everything except for the last value will be doubled up. 1 positive, 1 negative. All right? But it seems like we're only dealing with odd values. So after you plug in maybe the second or third value, you stop plugging in and you just start going with it. Because if I plug in a 3, I'm going to get 1 over 7 minus 1 over 9. And then you can continue the process until you get to the last entries. All right? And so you can do maybe just a plus 1/9 just to have it. And then do a plus dot 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 plus. And then it's up to you, but maybe just to demonstrate it to yourself, you do an entry just short of the nth term. All right? So if I were to plug in an n for n, this is what I would get. But if I were to go 1 short of n, that would be plugging in an n minus 1. All right? So I can do 1 over 2 times n minus 1 plus 1. And then minus 1 over 2 times n minus 1 plus 3. But honestly, on a test, I wouldn't do this if I knew it was telescoping, because I know that it's gonna terminate with it's gonna collapse to just the first and last term. So I'm just doing this to kind of prove it to myself that this works. If you're the kind of person that just believes everything that you're told, then don't worry about it. All right, so one of the most fun things in algebra is just canceling the living daylights out. And you might look at this and say, how do I know to cancel this? Well, if you know that consecutive values are going to cancel out, it's really just a question of what's going to cancel at what towards the end of the line. If I distribute the 2, 2n minus 2 plus 3. Negative 2 plus 3 is 1. So this would simplify down to 2n plus 1, negative 1 over 2n plus 1, positive 1 over 2n plus 1, cancels away. So all of this cancels right on down to 1 over 3 minus 1 over 2n plus 3. All right. So again, if a series collapses to a finite sum, then it converges by the telescoping series test. All right. So it just collapsed to a finite sum, converges by the telescoping series test, and it collapsed to a finite sum. And the question might be like, okay, how do you know it's a finite sum? Well, my answer to that is if you tell me what n is, I can tell you what the sum is. Right? That's what it comes down to. Now, if you want to find out what it would be if n approached infinity, then you could find a limit. And actually, I was going to do it, but you don't even have to bother. Right? It's just going to collapse down to 1/3 because everything afterwards you can see is getting subsequently smaller and smaller and smaller. So if this is going to, if all of this stuff is going to cancel down with one another, then this value here, the very last term of the sequence, is going to be 1 over infinity, basically. And so if that's the case, that very last term is going to go to 0, so this is all going to collapse down to 1/3. But again, determine whether it converges, not determine what it converges to. All right? Now, you could have attempted this with the nth term test, again, for convergence or divergence. So if you try that initially, you find the limit of all this stuff, what ends up happening? And I'll just show you real quick. I'll just kind of tuck it in there. Try the nth term test, because you never know. If you find the limit as n approaches infinity of all this business, you're in for like a little bit of a rude awakening. The result would be equal to 0, all right? Because you'd have 1 over infinity minus 1 over infinity. 0 minus 0 is 0. That's the worst possible outcome when it comes to the nth term test. That's telling us it's inconclusive. All right. You're not rooting for any particular outcome when it comes to these types of tests. Like, you don't care if it converges or diverges. You know you got to come up with one or the other. Whichever one it is, who cares, right? It's when this comes up, that's when you got a problem, because that means you got to do something else, because you do have to draw the conclusion. It's either going to converge or diverge. If it shows inconclusive for one particular test, you got to do a different test. All right? So we've tried the nth term, we learned about the nth term test, we learned about the geometric series test, we learned about the telescoping series test, and so now let's talk about the integral test. And like I said, this is where we'll finish up for tonight. You could see that one of the base components of the integral test, without stating the obvious that it involves an integral, is that we're talking about an infinite bound, all right? Which means that we're dealing with not just an integral, but an improper integral. So the skills that we reviewed in the beginning of class today are going to come back in a big, big way. All right, so what the integral test is telling us, it's saying if f is positive, continuous, and decreasing, so you're going to test all those conditions, for x greater than or equal to 1, and a sub n is equal to f of x. All right, that's not really 100% true. That's just how the theorem is stated. It's really more like a sub n can be approximated by f of x. All right, then the sum of a sub n and the improper integral going from 1 to infinity will either both converge or both diverge. All right, so what's happening here is we're using this integral. This is going to approximate the sum. All right, so what we end up showing is one of two things. Either that integral is going to converge or it's going to diverge. Its outcome will be consistent with convergence or divergence for the infinite series. All right. So how can that possibly be? Well, if you really think about it, let's say, I mean, for this case, what are we looking at? N over n squared plus 1. I would just get a quick sense of the sketch. It doesn't have to be perfect. N, or x over x squared plus 1. Say that. Fucking bit's killing me. Ah, I should have known that. So this is what f of x equals x over x squared plus 1 looks like. All right. Now, I only care about 1 to infinity, so there's a lot of stuff I'm going to ignore here. All right. So I would start here at 1 and go to infinity. So I would get all of this area if I were to integrate this function. All right. So that would be the antiderivative from 1 to infinity of f of x dx. All right, now a sub n equal to n over n squared plus 1. That's different, right? But not crazy different. It's just different in the way you would plot it. All right, so all right, so that's what roughly, I mean, it's like, you know what my graphs are, they're not good. But this is the function, and if I were to find the integral, I would get all of this area. All right, now what we would be looking for here, it's kind of a weird thing, because the sequence values are just the heights at any particular n value, all right? So this is n against a sub n. If I'm looking for the sum, what I would be doing is taking each one of these heights. So this height, this, this, and so on, all the different heights that could exist all the way up to infinity, and adding them together. All right. Now, each one of those heights could be considered, if you really think about it loosely, the area under the point. All right. But how do you find area under a point? Well, it's just a vertical distance. All right. And in fact, when we were coming up with the definition of area under a curve, it was all those little vertical distances with infinitesimal width giving us areas that we would use to approximate the area under a curve, and then we would limit it so that it went down to 0 in terms of its thickness, and then take the sum of all those things. So basically what I'm getting at is this is overkill. we're getting a lot more out of this than we would ever expect to get from this. All right. So if I were to find the antiderivative over the interval of 1 to infinity, I'm going to get not just 1, 2, 3 all the way up to infinity in terms of positive integers. I'm going to get 1.8, 2.01, pi, you know, like every decimal value in existence also. So it's going to be overkill. I'm going to get way too much. All right. But one thing that we can rely on is if this area is converging on a particular value, then these sums must also be converging on a particular value, because the nature of the function has that it's decreasing, so it's closing in on a particular value for the sequence, so its area is limited to a particular finite value. The same would be true for the sum of each one of these heights, all right, or the sum total of all the heights, all right. The opposite would be true also. If this were increasing without bound, then my area, I would not be able to contain an area. So it would be boundless. It would be inconclusive. It would be divergent. So if my function doesn't contain a finite area, then my sums will never be finite in general. Right? There's no way I could ever capture a finite value. Right? So that's really more theory than practical application. Really, what I need to do first is demonstrate that this is a decreasing series, all right? So grab it from the calculator. We're talking 1/2, 1/5. I'm sorry, decreasing sequence. 3/10, etc. All right, it's getting smaller and smaller. All right, we're going to let f of x equal x over x squared plus 1. That needs to be continuous and positive. Yeah.
1/5 is lower than 3 times.
There we go. Let me clean that up a little bit. All right, so we're going to let f of x equal x over x squared plus 1. This needs to exist on the interval. All right, so this function is continuous. Continuous. On negative infinity to infinity. That's overkill. I don't need to exist. I don't need it to exist on negative infinity to infinity. I just need it to exist on 1 to infinity. All right, so that's fine. We've met the conditions necessary. So now what I want to do is integrate this on the interval of 1 to infinity. We'll have x over x squared plus 1 dx. All right. So that's actually really not difficult. All right. We do have to clean it up a little bit and write it as the limit as a approaches infinity, going from 1 to a, of x over x squared plus 1 dx. Which is going to be the limit as a approaches infinity. So all those practice problems you did for homework, and all the stuff we went over today, it's coming in handy. You do use substitution here, but I recommend use substitution on the fly, because if I were to take the derivative of the bottom, what would I get? 2x. All right. That's only off from being the top by a multiple of 2. All right. So I know that it's going to be a natural log, x squared plus 1. If this were my function, that would give me double what I want. So cut it in half. And we go from 1 to a. If you don't like that, let u equal x squared plus 1 and go from there. All right. Clean it up. Cleaning it up is not too crazy because you're just plugging in the a and 1. And then, like I said, with limits, it's up to you. If you want to put it in your calculator, go for it. All right, so limit as a approaches infinity of 1/2 ln a squared plus 1 minus 1/2 ln of 2. Now, a very important question, a very, I would say, meaningful question here would be, well, what are we looking for? All right, so we're looking for a limit that exists. If it exists, then we're converging. All right, if the limit does not exist, then we're not converging. So that's really the big challenge at this point. So you can go to the calculator and take a look at this, or you can really start kind of getting into like the algebraic aspects of it, but I would say there's probably more trouble than it's worth. Because if you were to just kind of reason it out, and even if you don't want to like reason it out, you could do it numerically. One way or the other, you should be able to get it. Right? If I plug an infinity in for a, that's going to give me an infinity. Right? The natural log as I go out to infinity is going to approach what? Infinity. All right? The square root of infinity, or 1/2 of infinity, however you manipulate this, is still going to be infinity. All right? So I'm going to get infinity minus 1/2 ln 2, which is going to be infinity. All right? So therefore, the series diverges by the integral test. All right, and that's because the limit is not finite. You don't want to say the limit does not exist, because you start getting into philosophical issues. And it's like, does it not exist? Well, I'm showing that it's equal to infinity. So that's my limit. You might say that that means that there is no limit, but I don't think that's the case. Right? I disagree. Right? So for b, 1 over n squared plus 1. The good news is for this one, you're not going to have any trouble with the integral. We need to demonstrate the important characteristics, and that's that it's decreasing. So the first few values are sufficient. So we're talking 1/2, 1/5, 1/10. All right, so it's decreasing. We're going to let f of x be equal to 1 over x squared plus 1. So that's continuous on the interval of negative infinity to infinity. All right, there's no location in which this function would be undefined. So there's no way to make the bottom equal to 0, and there's no way to make it imaginary because there's no radical. All right. So if you want to skip one step, it's fine. You can jump right to the step where we're saying the limit as a approaches infinity, going from 1 to a, because it's consistent. It's going to happen every time you apply the integral test. It's always going to have this structure, so I'm fine with you doing it this way. Of 1 over x squared plus 1 dx. What is the antiderivative of 1 over x squared plus 1? Not ln.
That's arctan.
That's an arctan, yeah. Arctan, very good. Arctan of x on the interval of 1 to a. All right, so this is going to be the limit as a approaches infinity of the arctan of a minus the arctan of 1. And we did something very similar to this before. Arctan of a if a were to go out to infinity. All right, so one way to handle it, I showed all the numerical ways you can handle it. One way to handle it is to put something really large in for the arctan of a and see what multiple of pi it is. All right, other ways involve coming up with a graph and things like that. But what would you expect it to be? Pi over 2, yeah. Now, what is the arctan of 1? Not 0. Arctan of 0 is 0. Pi over 4, yeah. So this actually ends up being pi over 4 as a final answer, which tells us that the series is going to converge. By the integral test. The limit is finite. Or you could say the limit exists. The explanation only gets funky when you start getting into the ones where it doesn't exist, when it's divergent. So the remainder approximation, very easy. So this relationship isn't bad. It's used to actually determine what the approximate sum would be for, I still got this example to do, so it's still part of the integral test. So R sub n equals S minus S sub n. It's kind of a weird rule. It's not that bad, but it's telling us that if I modify it slightly, that we're looking at S sub n plus R sub n being equal to just an S, right? And so what that means is that you can get a partial sum that could be an adequate approximation for the actual sum of the series. Because what I was saying before is that generally we want to know if it converges or diverges, because technology gets us the rest of the way. The reality is, if you know it converges, then you start getting into the idea of finding an approximation of the sum, so that you don't have to kill yourself trying to figure out what the actual sum is, because that could be more trouble than it's worth. All right? And so this is a very easy process, but sometimes it catches people off guard because it doesn't always seem like it's something that you can do. Approximate the sum of a convergent series by using 6 terms. All right? So what that's telling me to do is list out the first 6 terms of the series. So 1 over 1 to the 4th, 1 over 2 to the 4th, 1 over 3 to the 4th, 1 over 4 to the 4th, 5 to the 4th, and 6 to the 4th. All right. That result is what we call S sub 6. That's the 6th partial sum. What I want to determine now is whether that's an adequate approximation approximation of the sum of this P series. Well, regardless of what the series is called, it doesn't matter. All right. So I'm just going to get these values. And then add them up. So I'm just doing it fairly quickly because it's just a matter of plugging and chugging. Talking about approximately 1.08. I'll go 3 more. 112. All right. Now we want to know, is that a reasonable approximation? So that's the second part. Include an estimate of the maximum error of your approximation. So what we would do, if I wanted the full sum, is I'd find the integral going from 6, the sixth term, the rest of the way to infinity, of 1 over n to the fourth. I'm sorry, 1 over x to the fourth, because it's got to be in terms of x. All right, so we're just using the same concept, except instead of going from 1 to infinity, I'm finding the number of partial sums that I want, or the term of the partial sum that I want, and then using my integral test approach to figure out the rest of the way to infinity. All right, and so I would find the limit as a approaches infinity on the interval of 6 to a of x to the negative fourth dx. So that's going to give me negative 1/3 x to the negative third on the interval of 6 to a. So negative 1/3 a to the negative third plus 1/3 times 6 to the negative third. The idea being that I want to find the limit of that as a approaches infinity. All right. Now, because this has a negative exponent, this is going to end up being negative 1 over 3a cubed. The other part is 1 over 216 times 3, 648. What's the limit as a approaches infinity of negative 1 over 3a cubed? 0. So 0 plus the constant is just going to be the constant. So that value there, that's our r sub n, in this case r sub 6. That's the remainder in the sum after the sixth partial sum. So the remainder, if I were to add up 1 over 7 to the 4th, 1 over 8 to the 4th, all the way to 1 over n to the 4th, add all those up, it would amount to no more than 1 over 648. All right, 1 over 648 is a very, very small number, which is telling me that this number here, my approximation of that summation, that infinite sum, could only be off. If it's off, it could only be off by at most 1 over 648. Would you say that's a bad number then? A bad approximation? No, not at all, right? 1 over 648, that's pretty good. All right, so it's a very, very small percentage, right? Obviously, the more terms you include, the smaller this fraction is going to be. But what this is telling us is that if we know that a series converges, then we can get away with only finding a certain partial sum, and that'll give us a good, reasonable approximation of what the overall sum is. within a very small fractional deviation. All right. So that's where we're leaving it for tonight, and tomorrow we'll do more.